Well, hello everybody, Dave here, and today we're going to start a series of lessons on modeling distributions of data. And what we're going to do is we're going to start performing the statistics necessary to take different values and compare it to something by which we can make meaningful conclusions. We'll do this in terms of ranking, and we'll also do this in terms of a generalized distribution known as the normal distribution or density curve in general. But before we get started, I wanted to take a look at one thing that came from Chapter 1. And let's say that we're collecting the data on the way that people go to the hospital based upon the type of accident that they have. We have two tables here that show serious accidents and less serious accidents, and then the mode of transportation being either a helicopter or some method of road transportation. That could be a person driving you, that could be an ambulance. Well, if we decide for ourselves which one we would choose based upon this data, you might look at the first table on serious accidents and see that the percentage of people that survive the accident is higher when you take a helicopter over some sort of road transportation. And if you look at the less serious accidents, you can see that by percentage alone, this is still the case, that taking a helicopter results in a higher survivability relative to that mode of transportation. So it would seem to be that taking a helicopter was your best chance at surviving. However, if you take the two tables and you combine them together to just talk about all types of accidents in the mode of transportation, now we have percentages that actually show us road transportation is the higher chance at survivability. And that's interesting that the first two tables showed clearly that by percentage alone, helicopter was the best mode of transportation, but when you put the two tables together into one table, now it's road transportation that is the higher percentage of survivability. Well, this switch of association from helicopter to road is the essence of what's known as Simpson's paradox. And the basic idea here is because we had such a high count number in the less serious accidents when it came to road transportation, that even though the helicopter's percentage was higher in that case, when you put the two together, because there was so many more people that survived based upon the road transportation, the overall result here is we're comparing 200 people that took helicopters to 1,100 people that took the road transportation. In this case, the actual percentages switched. So Simpson's paradox is the idea that it looks like this one variable is going to be the right answer until you put the two tables together and you find out that it actually switches. Quite a neat thing when it comes to statistics. So let's go ahead and get into the lesson now. And if there's anything you've learned from statistics so far, it's that the idea of comparison is very important. We have to have something to compare our observation to if we're going to determine if there's any sort of statistical meaning at all. And so one of the easiest things to talk about when it comes to comparison is this idea of percentile. And the classic example I like to use is SAT scores. And the idea that when you take the SATs, you actually get a scoring card that tells you, among other things, your raw scores in each subject, as well as the overall score, and then most importantly, your percentile. Because the truth of the matter is, if you get a high score on something, but everybody got a higher score than you, then is your score really that important or not? The example I used in class was imagine getting a 95% on a test. And that sounds fantastic, except for that ends up being the lowest score in the entire class. And does that mean that that's a good score? Or relative to the rest of the class, did you maybe struggle on something that you shouldn't have? And so this idea of comparing your score to everybody else's score is the essence of percentile. And it's essentially giving you a rank relative to everybody else's score in that given thing. So if we use as an example this student Jenny earning a score of 86% on her test, looking at the distribution here in the stem plot, we can see that her 86 is rather high compared to the rest of the test scores. And if we count all the data behind it, we can see that Jenny beat 21 out of 25 of her classmates. And based upon her rank, 21 out of 25 is 84%, which means that Jenny is at the 84th percentile. When we're talking about percentile, we mean position relative to the rest of the scores. So in this case, the idea that it is at a position is important. So she is at the 84th percentile. So this ability to rank our score versus the rest of the distribution score is very important. And from this, we should be able to create a graph that allows us to visualize this concept. And for that, we have to find the cumulative relative frequency. And what we will do is we will create a graph known as an ogive. Here's how it works. Let's say that we're looking at the first 44 presidents and their ages at inauguration. I've gone ahead and taken a table and organized it in such a way that you can see the frequency based upon a bin size of 5. Now that we have these values, to find the relative frequency, well, that's just simply taking the fraction. And so since in this case we're dealing with the first 44 presidents, we simply take our frequency, divide by 44, and turn it into a percentage, which you see before you. But now I'm going to look at it in terms of a cumulative frequency. And for that, the way that you do it is you take your first frequency, which is 2, and you add it to the second frequency, which is 7, to give you your cumulative frequency for the first 2 bins of 9. When you look at the third frequency, you can see now that what we've done is we've taken that 9 from the first 2, added it to the third, which is 13, to give you the cumulative frequency after 3 bins of 22. And you can see through the rest of the column that we continue to create the cumulative frequency until we get to the bottom and we have a count of 44. That's the signature that you've done the cumulative frequency correctly, because you should end up with the complete data set once you get to the bottom. That means to find the relative cumulative frequency, all we do is we take the fraction relative to the cumulative frequency instead of the regular frequency. And so you can see now that the percentages are going to increase until you get to the very bottom of the column, which is 100%. The relative frequency column, the signature that you've done it correctly, is the sum of those percentages should equal 100%. But in this case, you can see that if we took the sum of these percentages, we would end up with something much higher than 100%. So please recognize the fact that the cumulative relative frequency does not end up being a model by which we should add up to 100%. But the last quantity in your cumulative relative frequency should be 100%, since we now have the full data set of 44 divided by the full data set of 44. So now that we have our table done, we can actually create our ogive. And the first point that we have there looks like we're breaking a lot of graphing rules because our horizontal axis starts at 40. But with the ogive, the whole idea here is we're trying to create a graph for percentile purposes. So it makes sense that we start at 40 because the lowest value on our bins is at 40. Well, why then do we have a 0 there? Because there are no ages lower than 40. So that point there represents that 40 is at the 0th percentile because there are no ages below 40. As we move to the right on the ogive, you can see that these points are being graphed at the percentages that you calculated in the cumulative relative frequency. For example, if you look at the age of 55, that point there is at the 50th percentile. And that makes sense because if you look at the bins, we can see that 55 is higher than half of the data. And so 55 as an age is at the 50th percentile. Now the point that looks a little weird is the one at 70 because there is no 70 on the data. Well, if we just calculated percentile from the data alone, we wouldn't be able to come up with a 100th percentile because there would always be one point not included below you, which would be your point itself. For example, let's say that the highest age of the president at inauguration was 69 years old. Well, that age would be higher than the rest of the data, but that means that only 43 data points would be below it. So how do we create the 100th percentile? We simply pick an age that is higher than all the data that we have, and in this case, the next age from 69 is 70, and we know that 70 is not the age at inauguration for any of the presidents, which means it beats 44 out of 44 presidents on this table. And that's how we get that point at 100th percentile. So what does this now mean? Well, if we look at this graph, there's a couple things that we've done that, again, are very anti-graphing rules. The first thing is we're connecting the dots. And you don't normally connect the dots because to connect the dots is to state that that line is meaningful to the distribution. Well, in this case, for the mechanics of what the ogive is for, those lines are essential because you can actually read the percentile by simply drawing lines up to that line and then across to the vertical axis to figure out what the percentile is. For example, if we wanted to find out what age results in the 60th percentile, we would draw a horizontal line from the 60 over to that line that's on an angle, and then draw a line straight down to see that it's somewhere around 57 years old. So the moral of the story here is, unlike other graphing situations you're in where you would create a nice smooth curve, you want to connect the dots with straight lines because those lines are what's going to help you actually find the percentile for that particular score. So the ogive is a fantastic graph for finding percentile. If you have a TI calculator, I would encourage you to learn how to create these using lists and your stat plot utility. Now, if I go back to the SAT example, one of the problems about the SATs is they happen year after year after year. And so when I wrote the SATs many years ago, I got a score that would be difficult to compare to scores now simply because they're different distributions. It's a different test, it's a different number of people, it's a different overall mean to the scores. So, how do you actually compare my score to somebody else's score to find out if my score is better or worse? And the answer to that is we actually have to standardize the score. And the way we do so is this calculation here, which is known as the Z-score. And for statistics, the Z-score is vital because what we're doing now is we are taking scores from different distributions and we are standardizing them in such a way that we can actually plot them on the same distribution and compare the scores directly. So instead of just comparing the raw scores, which is a big no-no, we're going to take those raw scores, make them all standardized scores, and then we would be able to tell just based on the idea that the higher score would win. So to show the calculation briefly, let's take a look at Jenny's score again. And let's say that the class average was 80% and the standard deviation was 6.07. To calculate her standardized score, we would simply take the observed value, which is 86, subtract the mean, which was 80, and divide by 6.07, which is 0.99 total. Now, as you will learn in the next lesson, that 0.99 is very meaningful because that means that it is almost one standard deviation away from a mean of 0. And that's going to be a vital understanding because when we start talking about the normal distribution, the number of standard deviations away from the mean will become very meaningful. Now, if you noticed from the Z-score calculation, we did something that you've probably done in a different math class before. We took a value, we subtracted a constant, and then we divided by a different constant. And this is very much the type of transformation technique that you use when you're dealing with functions. So in statistics, the trick to adding and subtracting and multiplying and dividing by a constant is understanding what effects it has on the overall distribution itself. And first, we'll talk about this idea of adding a constant. And the basic idea between adding a constant is you are translating the distribution from one point to another. And what that means is your center is certainly going to change and your overall location is going to change, but the rest of the distribution itself will not change, specifically the range, the IQR, and the standard deviation. The shape of the distribution doesn't change either, but the shape argument you got to be careful with because it doesn't need to be a carbon copy of the original distribution, but it needs to look basically the same thing even if you've stretched it out or squished it in, but the overall shape of that distribution remains the same. So let's see if we can track transformations taking place on a distribution. When Australia switched over from the imperial system to the metric system, a class was asked to guess the size of their room in meters, and these are all the guesses that they had. I would encourage you to create a box plot and do the 5-number summary, mean, and standard deviation calculations for this data set, and track them as we move through the different transformations. I will use dot plots to describe this, and the first thing we're going to do is show a transformation taking place when we take the original data set and subtract from it a constant. Because let's say instead of wanting to graph the guesses, we want to graph the error in the guesses. So if we know that the actual room size is 13 meters, then the guess minus 13 will be the error. The dot plot that you see before you represents these two distributions. The top one represents the error calculation. The bottom one represents the original guesses calculation. The bottom table there shows you the various numbers that I told you to calculate before with your box plot, and what you can see are the numbers that are the same and the numbers that change. Well, you can see fairly clearly here, just based upon the dot plots, that everything looks to be the same except for the fact that the graph has been translated backwards. And that makes sense because we took every single data point and subtracted 13 from it. And because of that, nothing else is going to change. The table represents that very clearly, that although the position of the graph changed, if you look at the IQR, if you look at the standard deviation, those are identical, which means that nothing else has changed besides this shift backwards, which is exactly what we figured was going to be the case anyways. Now let's track the changes that occur when we multiply or divide by a constant. In theory, multiplying by a constant is going to change a lot of different things. And we already know that the center changed when you add or subtract a constant, but now that we're multiplying by a constant, everything is going to change except for the shape. And that should make sense because of the relative scaling that would occur. If you multiply 2 by 2, you get 4, but if you multiply 20 by 2, you get 40. So the scale difference is going to result in some sort of stretching of the overall appearance itself. That doesn't change the shape of the distribution, but it certainly changes the spread, and it changes the position of the overall points. So if we go back to our Australian data, let's say that we have our error calculations and we want to convert them into feet just to show the students how far off they were. Well, for that, we're going to multiply our data by a constant, in this case 3.28. And if you look at the dot plot now, you can see the top dot plot is the original calculation of the error in terms of meters, and the bottom dot plot is the error in terms of feet. And you can see that the distribution has been stretched out quite a ways, and the overall shape of this distribution looks the same even though it's stretched out. But you can clearly see that the center has moved, the spread has moved, and if you look at the table below, you can verify that with all of these different values that you now have. And so it's important to recognize that when you add or subtract a constant, it simply translates the distribution. But when you multiply or divide by a constant, you transform the overall distribution, and besides the shape, everything is going to change as a result. So that's it for this lesson, folks. Go back and take a look at that ogive again. Make sure you understand what percentile means. Recognize the fact that if you had data with the same score at a given percentile, we still just simply count the data points behind. So if we go back to our Jenny example, we had a score of 86. If there was 6 people with a score of 86, we would still just simply count all the points behind 86 because all of those values would be at the exact same percentile. Best of luck to you with your studies, and we'll see you again.